Okay, so we have the picture of one R3 and another R3. Of course, this picture doesn't just apply to R3, just in our example. So we have V, which in this case is R3, W, which in this case is R3. And I choose R3 because it's easy to visualize some of these things in R3. But there's nothing in any of the operations that we use here that doesn't apply in spaces of any dimension. Okay. So, thinking R3, but understand it could be anything. We have the picture that, let's say we have our W space here, and we have the range of A, or the row space of A, and the null space of A, which of course contains the origin, the zero vector. Now I've got a statement here. I'm going to spend most of the rest of the time explaining, and then we'll see what this statement means. Here's our picture. We've got V, we've got W. Now in this case, I've chosen for no good reason to look at the transformation T prime defined by the transpose of our matrix A. So here's our transformation T prime. And over here in V, we've got the row space of A transpose, we've got the null space of A. Two of our four basic subspaces. First place, we want to establish that the only place these intersect is at the origin. Now I know I've got this looking like it's a subset of this, but this is in 3 dimensions, and this whole thing could be turned perpendicular to this whole thing, and there's no good way to draw it, although there's a way with straight lines and planes to sort of represent it, and we'll see that later. So even though it doesn't look like it, these things have an intersection that consists just of one point, the zero vector. One vector. Okay. Remember that N of A is the subspace of V that maps to the zero vector over here. That's indicated by the blue. And that the range of A transpose is the image of the entire space W within the vector space V by the transformation T prime divided, represented by the transpose of our original A matrix. Okay, why do these things not intersect? Well, I'm not going to prove it because it's just an introduction here. Maybe we will prove it because it's an interesting proof. But the row space of A transpose is the column space of A, since the rows of A transpose are the columns of A. And make sure we understand that statement. Now, if X is in the column space of A, I'm just claiming that X is not in the null space, because if you take a column of A, it doesn't map to 0. So maybe I should make a little statement here. The columns of A don't map to 0, and I've just demonstrated that. Here's the A matrix we happen to be using. First column is this. If we multiply A by this first column, if I did the multiplication right, we get this. If we multiply the second column on the left by A, we get this. And the third column, we get this. And I didn't even write out what it is, but it's not 0. You can verify it. And then you can think about why it could never be 0 for all 3 vectors. Okay, once we've established that, and ignore this down here, this kind of follows from what we did over here. Doesn't follow, but by analogy, I guess it sort of does. Okay, so now we've got this picture. of our V, or our W in this, no, this is V, of our V, which is an R3 space, and we got a vector in that space. Well, I'm claiming that there is a unique pair of vectors, one in the null space and one in the range space of A transpose, such that this plus this equals this. Now, it's kind of easy to at least understand that intuitively. If you think of R3, and you think of the situation for this matrix, where the null space has dimension 1, so it's a line, and then the range of A transpose is a plane, because it has dimension 2, because A has rank 2. So you've got this line and you've got this plane, and the line is not parallel to the plane. I've written it as perpendicular here. You might want to think about whether it has to be perpendicular. And of course that depends on your inner product. But you can kind of think of it that way. So you got a plane here anyway. Okay, some plane in R3 of some orientation, and then some line representing the null space. Plane represents the range of A transpose. The line represents the null space. All the vectors that map to 0 are along this line through the origin. Then we know that if we have any vector x, any vector out here, we can go parallel to that line until we hit the plane. When we hit the plane, then we've got a vector in the plane, which when added to the vector we got when we kind of projected this down to the plane, gives us the vector here. Okay? So I've drawn that. Here's your x vector. Here's your null space. In this plane, it's some undistinguished orientation. Does not contain this null space. The plane's a plane through the origin. The null space is a line through the origin. And they intersect only at the origin. Then you take this vector, x, that'd be like the vector from here out to here, and you follow the direction of n of A back to the plane. Then the vector from the point on the plane where that line intersects the plane out to the x vector is what we call x sub n. That's a vector that's in the null space. They might say, well, this vector doesn't look like in the null space. The null space is over here, and this vector is over here. Remember, vectors don't have a place. Okay, this is a null space vector. If I take this arrow and move it over here, it's going to lie on this line. Okay. Then the vector from the origin out to this point is in the range space. And it can only happen for one vector. If you follow the direction of the null space from this point until you hit the plane, there's only one point at which you can hit the plane. And that one point uniquely defines this vector x sub r. So intuitively, there is a justification for saying that any vector out here is a unique sum of a vector in the null space and a vector in the range of A transpose. So there's your x equal to xr plus xn. In this case, we can say that your vector space V, which is an R3 space, is what we call a direct sum of the null space and the range space. And direct sum simply means that any vector in V can be expressed as a sum of a vector in the null space and a vector in the range of the transpose, and that can be done in one and only one way. Okay, so it means that x in R3 is a unique sum of xr and xn. Okay, So V is null space of A, direct sum, range space of A transpose. W is what? Well, everything we did here, we could have done if I'd have drawn my arrows in this direction and had the transformation T. I'd have had the range of A over here and the null space of A transpose right here. And I could have made the statement then that W is the direct sum of this null space in this range space. Any vector here is the unique sum of a vector here and a vector here, and the argument would have been identical to the one I just gave. So there's your W is a direct sum of the null space of A transpose and the range space of A. And essentially what I've written out here, that R3, that W, I shouldn't be writing R3 there, I should be more specific, but the W is an R3 space. It's not exactly equal to R3. The W is null space of A transpose plus the range space of A, or the row space of A. Meaning that any Y over here can be written as a vector in the null space and a vector in the range of A. A vector in the null space of A transpose and a vector in the range of A. And that's going to be extraordinarily useful when we look next time at regression, linear regression. Regression means you got a vector over here that's too big to map exactly onto something over here, okay, but you want to see how close it is, and you want to find the closest possible vector, and you can use that to get the best fit straight line for a big data set. Or if you want, quadratic model. So we're going to see how that works out, but we need this machinery to do it.